Okay, where was I? All right, so STP, so easy. Everything at STP makes life so easy. What is the molar volume of any gas at STP? Well, that's on the periodic table here. 22.4 liters for 1 mole of any gas, so 22.4 liters. Calculate the volume of 2 moles. Well, if 1 mole is 22.4, then 2 moles is 44.8 liters at STP. That is the key thing here. STP makes life much easier. If a CO2 sample of gas occupies a volume of 50.5 liters at STP, how many moles? Well, we got to divide that 50.5 by 22.4 moles. Liters per mole. That gets rid of liters and gives us moles. And oh, where's my dang calculator? There it is. Low bat. 50.5 divided by 22.4 is 2.25. 2.25 moles of what? CO2. Might as well. We know what it is. Okay. So that's that part. Then we get into this part. What is the volume in liters of 2.75 moles at STP? 2.75 times 22.4 liters per mole. This is moles. That gets rid of moles and gives me liters. 2.75 times 22.4 equals 61.6 liters of whatever gas they're looking for at STP. If you have 6.45 moles of gas, any gas at STP, how many liters? Well, we're just fish in a barrel here. 22.4 liters per mole. Moles, that gets rid of that, and gives me liters. 6.45 times 22.4 equals 144.48 liters of gas. Okay, so now we get to the ones that are not at STP and don't use that nice clean 273 and 1 atmosphere. All right. 4 grams of hydrogen peroxide is placed in a sealed 250 millimeter container at 500 K. What is the pressure of the oxygen produced in atmospheres? Well, this goes completely. So what I need to do is go from 4 grams of H2O2 to moles of O2. Why am I doing this? Because you either have to do PV equals nRT or you have to do stoich first. If they give you grams of something, you're doing stoich first. If they give you moles of something, then we're probably using PV equals nRT. We'll check down there with that one when we get there. All right, so there are 32, 33, 34 grams of H2O2 and 1 mole H2O2. And then we have moles H2O2 and moles of O2, and that is 2 to H2O2, and that is 2 to 1. All right, 4 grams. 4 divided by 34, enter, divided by 2, enter. We have 0.06 moles, I'm going to call it. I'm just going to round that number to 0.06 because that's who I am and that's where we are at this particular juncture. All right, so what is the pressure of the oxygen gas? So now I have moles and I can plug it into PV equals nRT. I have M, 0.06 moles. I have R, 0.0821. I have the temperature, it's 500 K. I have the volume, this has to be in liters, 250 milliliters divided by 1,000 is 0.250 liters. And they want to know what pressure, so we have to solve for P. So P equals 0.06 times 0.0821 times 500 divided by 0.250 to get pressure on its own on the other side, 9.8 atmospheres. 9.85 atmospheres. And I could have used anything. I could have used any R value down here because they asked me for pressure, and as long as I knew that I was using the one for kPa, I would have gotten an answer in kPa. It doesn't matter. As long as if they're looking for pressure, you can use any of the gas law constant values. If they give you atmospheres, then you have to use the one that goes to atmospheres. Okay. Following combustion reaction, if we are given 2 moles of ethane at STP, how many liters of CO2 are produced? Okay, so we're at STP, so we have 2 moles of C2H6, and for every 2 moles C2H6, there are 4 moles of CO2, and for every 1 mole of CO2, there are 22.4 liters of CO2. Because this whole thing is going off at STP, so 2 times 4 times 22.4, enter, divided by 2, enter, 89.6 liters CO2. That's how many liters of CO2 we produced. At STP means we can do it in one big stoich problem, not having to do any PV equals nRT. But this is at 54 degrees Celsius, which is 273, 7, 12, 327 degrees Kelvin. Be good to get that out of the way. So we did a combustion, and they gave me 25.21 grams, so it looks like I'm going to do some 25.21 grams C2H5OH. It looks like I'm going to go to my whatever product they're looking for, carbon dioxide. So I'm going to go moles of CO2, because I need to plug that into PV equals nRT. Now they've given me a pressure of 728 millimeters mercury. That means I have to use the R constant for millimeters of mercury, which is the same as torr, 62.4. So we use 62.4 liters torr mole degree Kelvin. I know the temp. The temp is 327 K. And and we're fixing to find out the moles of CO2 here. So grams C2H5OH. So 16, 21, 22 plus 24 is 66. Let's do that for real. 12 plus 12 plus 6 plus 16, 46. What? 12 plus 12 plus 6 plus 16. 46 grams. Always 46 grams. Okay. Fine. 12 and 12 is 24. 29. Just tired of adding it up. Okay, and 1 mole C2H5OH. And we have moles of C2H5OH, and we have moles of CO2. This is the harder problem where we convert from one to the other. 2 moles of CO2 for every 1 mole of that. That looks like a math problem. 25.21 times 2 inner divided by 46 grams is 1.09 moles. So we now have this 1.09. Okay, we got everything we need. Times 62.4 times 327 inner divided by 728 inner. 30.72 liters of CO2. And that makes sense. There's 1 mole. I mean, it's not at 298, it's not at 273, it's a little more than that, so it's going to take a little more volume, but 1.09 moles. Everything else is pretty standard. 760. The pressure's a little low, so there's that, but this all makes sense. Make sure your answers make sense to you. Okay? I think, is that it? Is that all? Is that the last? Yeah, that's the last page. Let me go over the K and P one real quick. Just so we know. And so I have complete videos. Kinetic molecular theory tells us how gases act, and basically, let's have some CO2 in here. And we have vectors, and they go all different ways. And the average of all these vectors is called kinetic, or average kinetic energy, also called temperature. Okay. Gases, they can be expanded. Of course they can. You can move these as molecules as far away from each other as you want, so that's check. They can be compressed. Of course they can. That's how scuba divers work. That's how oxygen tanks in the hospital work. Of course they can be compressed. Their molecules will spread out through a room. Yes, you know this. If somebody passes gas in the room, it fills up the room, or at least it fills up that whole area, so molecules will spread. The molecules will be attracted to each other. Absolutely not. These molecules are considered to be very, 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 very small considering the space they're in. So we consider them to have negligible volume, and they do not interact even when they bounce off the side. It is an elastic collision. They don't lose energy. They don't stick to the wall. There's no attractive forces to the wall. They just bounce. Measurement of an average kinetic energy is called temperature. Mentioned that early. The average of all these vectors is temperature. When molecules collide, they stick together. Absolutely not. They do not. They don't interact at all. That's what kinetic molecular theory says. It says that gas molecules are lonely and that they are not touching each other or interacting with each other or sticking to each other. The measurement of average kinetic energy is called velocity. No, that's called temperature. You know that. It's right there. Molecules have elastic collisions between molecules and container walls. Yeah, and between each other. I guess that's what that's saying. Between molecules and between container walls, we have totally elastic collisions, don't lose energy at all. Gases are in constant random motion. Check, check, check. All right. So that is kinetic molecular theory. A couple of multi-select questions on there, and I know how you hate multi-select, but make sure it's clear in your head that these guys do not interact with each other, do not attract each other, are not attracted to the wall, are not repelled by the wall. There's a lot of room in there. They randomly move. Average kinetic energy is temperature. And if I have two gases at the same temperature, they have the same average kinetic energy because that's what temperature is a measure of. All right, guys, that is finally it. I will make a review video for the final exam, and then we are done. It has been such a pleasure teaching y'all. Y'all are so awesome. You are so smart. I mean, I'm not even joking. Y'all might be the smartest set of classes I've ever had because you just get it. Anyway, you guys have a great day, and I will see you on the test.